Hey y'all, welcome back. So today is the day where we're going to put together everything we've learned in this unit, and we're going to be able to evaluate trig functions of all the common angles that we talked about last time. So far in this unit, we've talked about angle measures and degrees and radians. We've talked about the different trig functions, sine, cosine, tangent, secant, cosecant, and cotangent. We've talked about Pythagorean theorem and your special right triangles. Last time we got into the unit circle, and today we're going to go over how to use the unit circle to evaluate those trig functions that we talked about earlier. So let's go real quick and just redefine what a unit circle is. It's simply a circle that has a radius of 1. So here's a nice little diagram for you. And very briefly, at the end of the last lesson, I'm not sure if it was on the recording, but we talked about it in class. We went through and talked about how these coordinates on the unit circle are related to the different trig values. So let me kind of go into a little bit more detail about that. So let's say you had some point on the unit circle, like right here, right? And you could draw a triangle by dropping an altitude and drawing this little hypotenuse here. And let's call, we don't know where this is, so what I'm going to do is I'm going to label the adjacent side as my x and the opposite side as y, so that this coordinate would just be at some arbitrary point x comma y. And because we're dealing with the unit circle, the hypotenuse is always going to be 1, and that's going to be helpful for determining the value of all these different trig functions. So for example, if I want to calculate the cosine of some angle measure, so let's say I want to compute cosine of, cosine of theta, for instance. Now cosine is defined as the adjacent side divided by the hypotenuse. Now let's take a look at our diagram here. The adjacent side is going to be this x, and the hypotenuse is just going to be 1, right? So if it's x divided by 1, it's just equal to x. So our cosine of whatever angle measure now I didn't label it. Let me go ahead and label theta in here. Theta is going to be this angle measure right in here. Cosine of this angle measure is going to equal the x coordinate along the unit circle. Similarly, we can define sine as being the y coordinate because, if I can throw in an equation here, sine of theta is going to equal the opposite side over the hypotenuse. And so the opposite side here would be the y. It's always that vertical side. And so that would be like y over the hypotenuse, which once again is 1. And so y divided by 1 is just y. So the sine of any given angle measure is equal to the y coordinate on the unit circle. Okay, so, like this x is this x. This y is this y. Okay, so you've already filled out your unit circle. And in fact, let me go ahead and bring it up so you can see see it while we're going through this. There it is. Okay, here we go. I'm just gonna hide this down here. Can I make it not? Oh well. Oh, there we go. Okay. There we go. So anyway, the cosine of whatever your angle measures, so let's say I want to know cosine of 120 degrees, I can just report back the x coordinate, this -1/2. If I want to know the sine of, say, 4 pi over 3, I'm going to report back the y value here. And this works for angle measures greater than 360 or greater than 2 pi, and also negative angle measures. For instance, if I want to know the sine of negative pi over 6, negative pi over 6 would be right here, I'm still going to grab that y coordinate, and it's going to be -1/2. So these two are pretty easy because they're just going to be the coordinates that we've already labeled on our unit circle. But let's talk about the other ones. So for instance, let's talk about the reciprocal functions, and then we'll get into tangent. So the reciprocal of cosine is secant. So secant of theta, lost my theta there we go. Secant of theta is going to be the reciprocal of cosine, so that will be 1 over x. If x is a fraction, and hopefully you can see. I'm not sure how I'm going to point to it, but if you look at all of your really, except for the extremes, they're all going to be fractions. All of the x values and even the y values of these coordinates are going to be fractions. So instead of thinking about it as like 1 divided by x, just simply flip the fraction over. Okay, so for instance, the secant of pi over 6, instead of being root 3 over 2, it'd be 2 over root 3, and then you'd rationalize. So just remember that that is the reciprocal of the x value. Similarly, a cosecant will be the reciprocal of the y value. So again, just locate the y value. It'll most likely be a fraction, and if it's not a big deal. Like the reciprocal of 1 is 1, and the reciprocal of 0, by the way, is undefined. So that'll come up, but let's cross that bridge when we get to it. So yeah, the cosecant's going to be the reciprocal of sine. Let's talk about tangent. Now, tangent is the opposite side over the adjacent. Right, so the opposite side would be the y, and the adjacent would be the x. So tangent, you're going to have to divide y by x. And as we go through some examples, you'll see it's not as bad as it sounds. You know, at first glance, you might look and say, okay, well, if I want tangent of pi over 6, for instance, you know, go look at the unit circle. If I want tangent of pi over 6, I'm going to have to do 1/2 divided by root 3 over 2. But it works out a little nicer than it might seem at first glance. And when we do some examples, I'll kind of show you how that plays out. And then finally, the reciprocal of tangent is cotangent, which will just be the reciprocal, so it'll just be x over y. Let's go ahead and type that out. The cotangent of theta is going to be x over y. All right. So that is like about as far as the notes themselves are going to go here. From here on out, we are just going to practice using our unit circle to evaluate all these different trig functions. So let's work on one at a time, one trig function at a time.
So here we have cosine, and we've got the cosine of several different angle measures. I'm going to go ahead and pull up our unit circle here, just so that we can keep an eye on where I'm getting all these values from. And I'll describe, at least for the first one, how I'm getting the values in terms of triangles. But I think you should really be thinking about the unit circle as well to make these problems go a lot faster. So cosine of 30 degrees, we can see that 30 degrees is going to be, or at least the terminal side of 30 degrees, will be at this angle measure right here. So if we draw a little triangle by dropping an altitude where that terminal side intersects with the unit circle, we've got a situation where we've got a 30, 60, 90 triangle, where the hypotenuse is 1, and since cosine is adjacent over hypotenuse, we really only care about this adjacent side, and we know that that side, because it's a 30, 60, 90 triangle, is square root of 3 over 2. So since cosine is the adjacent side over the hypotenuse, and I suppose I really didn't make it obvious what angle measure I'm talking about, but we talked in the last unit about angles in standard position. I'm really talking about this angle right here. This is going to be my theta. There's the 30 degrees is this mark I'm making right here. So cosine's adjacent over hypotenuse, and anything divided by 1 is just itself. So cosine of 30 degrees is root 3 over 2. Now, the one big trick here, especially since we've got the unit circle pulled up, is that cosine is always going to be equal to the x-coordinate of the point that the terminal side intersects on the unit circle. That's kind of the big trick, and that's kind of the whole point why we use this unit circle to begin with. It just makes finding these trigonometric values go a lot faster. So from here on out, I'm really just going to be looking at the angle measure and then pulling out the x-coordinate. So cosine of 120 degrees. I'm going to look for 120 degrees, which I see in quadrant 2. And I'm going to report back the x-coordinate at that angle measure, which you can clearly see is -1/2. Now we would normally, to really describe this, I would draw a triangle like I did in the first problem, using the reference angle rather than 120 degrees because they would have the same cosine value. And, we can't really draw a right triangle with 120 degrees, so we have to use that reference angle. But it's just going to go a lot faster here if we just start to get used to looking at the unit circle and reporting back the appropriate value. So we're going to just keep doing that. So yeah, cosine of 120 is -1/2. Cosine of 510 degrees, move this unit circle out of the way here, kind of getting in the way. Or you know what, maybe I'll put it over here in this little corner over here. Cosine of 510 degrees. Now 510 degrees we don't see that on the unit circle itself. That's going to be greater than 360. So what we need to do is find a coterminal angle, and we can do that by subtracting 360 from 510. So 510 minus 360 is going to be 150. So this is actually going to equal cosine of 150 degrees. So once we establish that this is equal to cosine of its coterminal angle, we can actually find 150 degrees on the unit circle. You can see it right there in quadrant 2 once again. And the x-coordinate at 150 degrees is -√3/2. Bring that back down. So yeah, -√3/2 would be our answer for this one. Cosine of 45, or no, I take that back. Cosine of -45, although in this case it wouldn't really matter. They'd have the same value, but cosine of -45 is going to be equal to cosine of -45's coterminal angle, which, this one you can kind of just see visually, I think. 45 degrees is going to be, or -45 degrees is just going to be 45 degrees rotated in the clockwise direction. So it's going to be coterminal to -45 plus 360, which is going to be at 315. So cosine of -45 degrees is equal to cosine of 315 degrees. And the x-coordinate at 315 degrees is √2/2, which is actually the same thing as cosine of +45 degrees. And that's because cosine is an even function. We haven't really talked about that. Cosine's an even function, sine's an odd function. We really haven't talked about what that means or anything, but this is going to be an example showing, really demonstrating that it is in fact an even function. Okay, so anyway, so it's √2/2. Got caught talking, forgot to type it out. All right, so yeah, we're really looking at this angle measure right here. I'm going to try to highlight these on these last few. Okay. So anyway, there's cosine. Now let's talk about sine. So sine, I'll show just like with cosine, one using the right triangle, and then for the rest, I'm just going to pull the appropriate values from the unit circle. Sine of 45 degrees, the 45 degree mark is right here. And so if we do the same thing as we did with cosine, we can drop in altitude and mark up this triangle. It is a right triangle with a hypotenuse of 1. And the opposite side, which is the only one relevant to this problem, is going to be this square root of 2/2. And this is, once again, coming from one of our special right triangle ratios. So sine is opposite over hypotenuse. So here we get the opposite side, which is √2/2 divided by 1. And so sine of 45 is equal to √2/2. Now notice how this is the y-coordinate of the function, or of the coordinate on the unit circle. So for all of these, that's what we can do, is just look for the y-coordinate of the point where the terminal side intersects the unit circle and report that value back. So cosine is the x value, sine is the y value. So if we're trying to find sine of 150 degrees, we want to locate the y-coordinate where the terminal side of 150 degrees is intersecting the unit circle. So looking at our unit circle, we see 150 degrees is in quadrant 2. A lot of these are in quadrant 2, actually. Well, I guess there's only 4 quadrants, so there's probably going to be a lot in quadrant 2. So here's our terminal side right here, and we can see that the y-coordinate there is 1/2. For sine of 540 degrees, we already established earlier on that, oh no, that was 510. So I take that back. We did not establish the coterminal angle of 540 degrees. So let's talk about that. This is going to be 450 minus 360 is going to give us a coterminal angle. So 540 minus 360 is 180 degrees. So this is going to be equal to sine of 180 degrees. 180 degrees is going to be right here. And since the sine value is going to report back the y-coordinate on the unit circle, you can see that the y-coordinate is 0. So sine of 540 degrees is just 0. Negative 240 degrees. Well, that's another angle measure that's not explicitly on our unit circle, but we can find it by finding a coterminal angle. If we add 360 to negative 240, we get 120. So that means that negative 240 is coterminal to positive 120 degrees, which is right here. Oh, that's a square. That is not. Oh, that's pretty sloppy too. Let's try this one more time. There we go. There's 120 degrees is right there. So yeah, sine of negative 240 is equal to sine of positive 120. And the y value at 120 degrees is, if we zoom in here, you could probably see it a little easier, √3/2. You're going to notice that a lot of these answers are going to be the same. I mean, we're going to be seeing the same numbers kind of over and over again, whether it's 1/2 or √3/2, or maybe it's negative. √2/2. These are the kinds of numbers we're going to be ending up with. So yeah, so that's cosine and sine. Just to kind of summarize here, cosine is going to report back the x values, and maybe I'll just make a little note here. Cosine wants the x values on the unit circle. And sine wants the y values on the unit circle. So cosine and sine, these are the two easiest ones to evaluate because you literally just look at the unit circle and report back the values. As long as you can fill that unit circle out, these should be super easy. Where it gets a little bit more complicated is when we start looking at the other functions, because we're going to have to, write the ratio out and do some reduction, some rationalization of denominators. So it's a little bit more complex to do the other ones, but we're still starting off by looking at the coordinates. We just have to know what to do with them for the rest of these functions. So let's start with this one, and then hopefully it'll make, when I show you the triangle for tangent, it'll make a little bit more sense on how we get the rest of these values. So for tangent of 30 degrees, we want to be looking at the 30-degree mark, which is right here. And I'm going to drop my altitude from the unit circle down to the x-axis, draw my right triangle. My opposite side is going to be 1/2. The hypotenuse, make this a little smaller. The hypotenuse is just going to be 1 because it's the unit circle. It's sort of by definition. That's how we define that circle. And then the longer side here of this 30, 60, 90 triangle is going to be √3/2. Well, that's a double root there. We don't want that. We want √3/2. Might need to make that a little smaller, make it a little bit more legible. Kind of really squeezing it in there. Okay, so tangent is the opposite side divided by the adjacent side. So we would have, and I'm going to show you a shortcut here, but we would have 1/2, that's our opposite side, over root 3 over 2. And I'm going to really break it down on this one, but for the rest of these, I'm going to kind of show you a little shortcut. So here, when we're dividing fractions, that would be equivalent to multiplying by the reciprocal. So this would really be 1/2 times 2 over root 3. Now 2 over 2 reduces to just 1, so we can effectively cancel out these two factors, and we get 1 over root 3. So this is going to be 1 over root 3. This unit circle out of the way because I'm going to need a little bit more space because we need to rationalize this denominator. And so we need to multiply both of these sides, both the numerator and the denominator, by root 3 over root 3. And that's going to force that denominator to be rational. One times root 3 is going to be root 3. And then root 3 times root 3 is just going to be 3. So really our final answer is right here, root 3 over 3. Now I said I would give you a little shortcut for the rest of these. Notice how this was the y coordinate divided by the x coordinate. And that is how we're going to essentially evaluate tangent. So I'll just say tangent of theta is going to be the y coordinate divided by the x. Okay, if we make a similar statement for sine and cosine, we would say that cosine is just equal to the x coordinate, because it'd be x over 1, and then we would say sine is the y coordinate. So sine of theta would be just y. So since tangent is y over x, we can also say that tangent is really just sine divided by cosine. We're not going to deal with that Pythagorean identity, or that's not a Pythagorean identity, but that quotient identity quite yet. We'll get to that in the next unit, or in one of the coming units. But yeah, so all we need to do is divide the y coordinate by the x coordinate once we find that terminal side. Now, most of these are going to have 2 as a denominator, so this little canceling out of the 2's is basically going to happen every time unless you get one of these extreme values on the unit circle with the 1's and the 0's. So it's safe to just divide the numerators here. See, 1 over root 3 just became like 1 over root 3 because the 2's canceled out. That's going to happen on each of these coordinates inside the quadrants. So as you're evaluating this, the little shortcut is just to go straight to the numerators and divide those. And so that's what I'm going to do from here on out. Tangent of 135. Let's move this over now. I know this unit circle is getting moved around a lot here, but yeah, I want to make sure you can see it. So tangent of 135, we can see 135 is in the second quadrant right here. And so if we are looking for the y coordinate divided by the x coordinate, we can see that the y coordinate is root 2 over 2, and the x coordinate is negative root 2 over 2. So if we just ignore the denominators, because we know those 2's are going to cancel out, this is just going to be root 2 divided by negative root 2. And so that's just going to simplify to be negative 1. Anything divided by itself is 1, and then we got a positive divided by a negative is going to be negative. These sort of 45-degree, how do I want to say, these increments of like 45 degrees, 135, 225, and what's this last one down here, 315, they're all going to be 1 or negative 1, because take a look at those coordinates. There's some combination of positive or negative, root 2 over 2, comma, root 2 over 2. So when you divide the y by the x, it's always just going to be 1, or if the signs are different, negative 1. Tangent of 0. Okay, this one's a little interesting because 0 degrees is right here, and this coordinate is 1, comma, 0. So if we're going to try to evaluate tangent of 0, we have to do the y coordinate 0 over 1, which is just 0. Not much to say there. So tangent of 0, 0. Yeah, that's, I guess, not as interesting as how I thought that was going to go when I first saw it. I guess I was actually thinking of 90 degrees. So this one would be a little bit more interesting. At 90 degrees, which is up here, the coordinate is 0, 1. So here I've got to divide 1 divided by 0, which, as we know, and this might be a good video for me to make in the future, like why can you not divide by 0? But we'll just take that for granted right now and say you are not allowed to divide by 0. And so what we get is an undefined result. So we'll just say that this has no value, it's undefined, because we get a divide by 0 error here. So that takes care of the sine, cosine, and tangent functions. Now let's talk about the reciprocal functions. We'll start with secant, which is the reciprocal of cosine. So before we said that cosine of theta was just the x coordinate. And so secant of theta is just going to be the reciprocal of the x coordinate, or 1 over x. Now usually I'll recommend to not really think about it as 1 over x, because all of these coordinates, or the majority of them, are going to be fractions anyway. And instead just think about flipping the fraction. Okay, 1 divided by a over b is always going to be b over a anyway. So just cut to the chase, and for example, if cosine of whatever is root 3 over 2, just write that the secant is 2 over root 3, and don't bother trying to divide and do all that stuff. We'll just do that implicitly. So secant of 150 degrees, we can see that 150 degrees is in the, let's see here, the second quadrant, and it's going to be right here, 30 degrees shy of 180. Now the x coordinate at 150 degrees is negative root 3 over 2. So it's really going to be the reciprocal, or negative 2 over root 3. Now, just like we've done in the past, we do need to rationalize this, and that means we need to multiply it by root 3 over root 3. So 2 times root 3 would just be 2 root 3. And then root 3 times root 3 would just be 3. So secant of 150 degrees, I personally like this other answer better. I think it's a cleaner answer. But convention and just kind of tradition dictates that we do rationalize that denominator. I'm not a big fan because, look, I mean, we just are throwing out more numbers here, but that is how you'll see the answer more often than not. 315 degrees, let me move this out of the way. Sorry about that. 315 degrees is going to be in our quadrant 4 here. The same place as negative 45 degrees, or 7 pi over 4 radians, is right here. Oh, that is another rectangle. There we go. 315 degrees is right here. And we can see that the coordinates are going to be root 2 over 2 comma negative root 2 over 2. So the x coordinate being root 2 over 2 means that our secant value will be the reciprocal of that, or 2 over root 2. If I try to rationalize that by multiplying by root 2 over root 2, I'm going to get 2 root 2 over 2. It's too many 2's. But the 2's will reduce here. 2 divided by 2 is 1. And so this one actually does clean up nicely when you rationalize, unlike that other one. And we do just get root 2 here. I don't think this is very obvious or intuitive when you first look at it, that 2 divided by root 2 is just going to be root 2. But then if you think about it backwards, root 2 times root 2 is 2. So that does kind of make sense. Secant of negative 60 degrees. So negative 60 degrees is going to be coterminal to positive 300 degrees. So we're looking at the terminal side right here, which intersects this point, which is at 1/2 comma negative root 3 over 2. And so the reciprocal of the x value being 1/2 is going to be 2 over 1, which is just 2. Oh boy, here we go. Secant of negative 1,350 degrees. We're definitely going to have to find a coterminal angle here. That number is just too big for me to really wrap my head around where exactly that's going to end up. So to find a coterminal angle that's on the unit circle that we can use to actually work this problem out is I'm going to continue adding 360 until I get an angle measure between 0 and 360. So in my calculator, and you could probably do this by hand, but I'm going to use a calculator just to expedite the process, negative 1,350 plus 360. And I'm going to do that once, twice, 3 times. Oh, hold up. Nope. I pressed the wrong button on here. Let's see. Okay, I'm just going to start over here. What was it? Negative 1,350. I'm going to add 360 once, twice, 3 times, 4 times. If I add 364 times, in other words, if I do 4 positive revolutions, that's going to take me to a coterminal angle of 90 degrees. So secant of negative 1,350 degrees is equal to the secant of positive 90 degrees. Now the x-coordinate at 90 degrees is 0, so to reciprocate 0, we actually have to do 1 over 0. And we've seen a problem like this before, and basically I just said you're not allowed to do this. This is an invalid operation. You're not allowed to divide by 0. Again, the question, like, well, why can't you divide by 0? It was probably better left to another video. It deserves kind of its own explanation. But for right now, we'll just accept that this is going to be undefined. And that wraps it up for secant. So secant's the reciprocal of the cosine value, so we reciprocate x. And similarly, cosecant is going to be the reciprocal of sine, or the y-coordinate. Oh, gosh, look at that. That should be secant. So yeah, we'll take the sine value. Take this little sine equation. We're going to reciprocate both sides here. So since the sine of theta is the y-coordinate and cosecant is the reciprocal of sine, the cosecant of theta is going to be 1 over y. But just like with secant, we're not going to really think about it as 1 divided by a fraction. We're just going to flip the fraction. Okay, we're just going to kind of cut to the chase and get it done. So cosecant of 360 degrees, we can see 360 degrees is right here. The y-coordinate at 360 degrees is 0. So this is another case, just like the previous problem we did, where we get an undefined solution. So I guess that's a little contradictory. There actually is no solution. This does not have a value. Negative 330 is going to be coterminal to, what would that be coterminal to? To positive 30 degrees. So we can say that cosecant of negative 330 is equal to the cosecant of 30 degrees. And 30 degrees is going to be this first mark right here. The y-coordinate here is 1/2. So the reciprocal of that is 2 over 1, which is just 2. (270 degrees, or to be more specific, the cosecant of 270 degrees. 270 degrees is right here. The y-coordinate is negative 1. And so the reciprocal of negative 1, just 1 over negative 1, which is negative 1. The cosecant of 45 degrees, we got 45 degrees right here. And the y-coordinate at this angle measure, where the terminal side intersects the unit circle, is root 2 over 2. So the reciprocal of that is going to be 2 over root 2. So we get, I think we had that answer over here somewhere, so I might as well just copy and paste it. We do get 2 over the square root of 2. And then when we rationalize that denominator, the 2's cancel out, giving us just the square root of 2. All right, that's it for cosecant. So we're 5 out of the 6. We're done with 5 out of the 6 trig functions. The last one here is cotangent, which is the reciprocal of tangent. So since tangent was y over x, we can say that cotangent is x over y, because it's just the reciprocal. So cotangent of 225 degrees, we're going to look at the 225 degree mark, which we can see in quadrant 3 here. If you don't see it, it's down there. And the coordinate there is negative root 2 comma negative root 2 over 2 divided by negative root 2 over 2. Just like with the tangent, I'm going to ignore the denominators because they're just going to cancel out anyway. So this is going to be negative root 2 divided by negative root 2. Anything divided by itself is 1, so that's the value of cotangent of 225. The cotangent of 270 degrees. So 270 degrees is right here. And you can't see that because my unit circle is getting in the way. But here it is right there. Let's get this unit circle out of the way. I think we do we even need the unit circle anymore? I mean, we only got a couple left, so I'm just going to leave it up there. So, yeah, the coordinate there is going to be 0, negative 1. So if we divide the x by the y, the x here is 0, the y is negative 1. 0 divided by anything other than 0 is just 0. Cotangent of negative 210 degrees. So negative 210 degrees is going to be coterminal to the angle measure we get when we add 360, when we do one full positive revolution. Negative 210 plus 360 is 150. So we can say that this expression is equal to cotangent of positive 150 degrees. 150 degrees and negative 210 are coterminal. So this 150 degree angle measure, I'll make this a little bigger so you can see. We can see that is in quadrant 2, right here. Nope. Let's try that again. And so we want to do the x divided by the y. The x coordinate here is negative root 3 over 2, so I'm just going to do negative root 3 because just like with all the tangent and cotangent problems we've had already, the 2's in the denominator will cancel out. So negative root 3 divided by positive 1, right? Because it's negative root 3 over 2 is the x, 1/2 is the y. So it's like negative root 3 over 2 over 2. But again, the over 2's are just going to cancel out. So we'll just leave it as negative root 3 divided by 1, which will simplify as just negative root 3, because anything divided by 1 is itself. This is just going to equal negative root 3. Finally, cotangent of 60 degrees. We know where 60 degrees is, hopefully. Done enough of these to really get a good feel for where these angle measures should lie. 60 degrees is right here. We want to do the x divided by the y. The x is 1/2, so it'd be like 1/2, but I'm just going to write the 1 because I know the 2's are going to cancel out. So 1 over square root of 3 over 2. And again, I'm not going to write the over 2. I'm just going to write the square root of 3. So once we rationalize this, we've done this once already. Actually, we've done it several times. We need to multiply both the numerator and the denominator by root 3. So that'll end up with root 3 over 3. Now we did 4 examples of evaluating trig functions. We did all 6 trig functions, kind of going over how you come up with these. And really what you want to do here is you just really want to keep practicing that unit circle. Okay, like just keep at it, keep writing it down so that you can finish that unit circle in just a matter of minutes with no errors. And then all these problems become basic, kind of trivial. to be quite honest with you. As long as you can remember what each trig function is looking for, and you remember the ratios, those SOHCAHTOA kind of ratios, then you should be good to go. But yeah, that's it for today. Y'all, thanks for watching, and have a great day.